I want to talk to you now about the validation of measurement methods and their uncertainty. And although a lot of what I'm going to talk about is true for all air sampling of hazardous substances, there are fundamental differences regarding gases and vapors, vapor particle mixtures or pure particle sampling. So I will focus on the gases and vapors especially, and not will mention the different, because 10 minutes is not a lot of time to go into the differences. So if you focus on the measurements of workplace air for risk assessment, you have one number in the center, which is the measurement result, usually given as weight per volume number. For example, as a milligram per cubic meter. And this is the number that will determine if we're exceeding a limit value or not. And this measurement result is influenced by analysis and the sampling parameters. The ISO norm 22065 also gives us some framework for validation experiments for gases and vapors. For example, this framework for the minimum measurement range for these experiments, which is 0.1 times the limit value up to 2 times the limit value for occupational exposure limits, and 0.5 up to 2 times the limit value for short-term exposure limits. And otherwise, there are no prerequisites at this point, except that the limit of quantification for your method should be lower than the lower limit of your minimum measurement range. But we do strongly recommend that if your limit of quantification is much lower than this 0.1 times your limit value, that all the experiments I'm going to talk about will also be conducted at your limit of quantification. Otherwise, you've validated your method, but not really at the limit of quantification you're going to give. As we go a little bit more into detail, we see the reality is a little bit more complex than just the analysis and the sampling part of influences on the measurement result. And we can categorize these impact into 3 different categories. So we might find with our experiments they will have no impact at all on the measurement result, which is brilliant because no further action is needed. We might also find that they have a steady impact or a calculatable, quantifiable impact, which is also quite good because then it can be taken into account for the measurement result. But sometimes there's no consistent or quantifiable impact, or there's no reason to measure this kind of impact. And then this will be part of the measurement uncertainty, or in the worst case scenario, will even lead to the limit of the usage of a set method. So let's follow the sample of the hazardous substances in the air to the laboratory to the measurement result. So when we do that, we have to start, of course, with a sample holder. And there are questions regarding the sample type, the sampler type. What is the right kind to use for your application? You have to think about the wall deposits, how to increase the sampling efficacy. And these are all questions that will lead you to the selection of the right sampler for your application. But I want to emphasize 2 other components: the sampler capacity, which can be tested in the validation experiments, and the breakthrough volume. So the norm says that for a time-weighted average measurement result for the limit values, you have a sampling time of 8 hours. In Germany, we often use shorter times for 2 hours, and then you have your capacity experiments should be conducted at a minimum of 1 hour more than the sampling time you're actually using for the capacity experiments. If you don't use a sampler like the test tube behind me, which has an inbuilt control layer, you can put just 2 samplers of the same in sequence behind one another, and then you should measure your control layer, and your control layer should have a concentration less than 5% than the overall measured concentration to prevent the breakthrough. The norm suggests we should also test for the breakthrough volume, which is closely linked to the flow rate, as you will see later. But we find it often to be sufficient to test for the actual capacity of the sampler and not actually test the breakthrough volume. But the norm says it should be done. As far as environmental influences go, the temperature is only necessary for gases and vapors if you have a sampler that is sensitive to temperature. But for gas and vapor particle mixtures, it's essential because the distribution between the particle and the vapor is really strongly dependent on the temperature. And the experiments for both the temperature and the relative humidity are conducted at the extreme values, so extreme high and low temperature or humidity. But you have to test additional temperatures and humidities if you actually find these do have an influence on your sampling and your measurement results. You can also adjust this values if needed, if the use case of your methods is higher or lower temperatures, so you can adjust this. This temperatures is not the only temperatures that need to be tested. And if you look at the overall sampling volume is of course dependent on the flow rate and the sampling time, which are subject to the read-off accuracy of your stopwatch, of your flow meter, but also on the stability of your pump, of your flow rate. And these are actually quite good examples for things that are usually taken into account into the measurement uncertainty. And after sampling, we have the hazardous substance on some kind of filter or test tube, and then it needs to be transported into the laboratory. Loss only occurring during transport, not due to stability issues, but due to the actual transport, should be prevented. You should select a sampler that no losses will occur. And we operate under the assumption that 100% of the substance will get to the lab only with regard to the transport. With regard to the stability, you need to conduct experiments for the stability after sampling, and you should test these at the worst case scenario. So you have like really high and really low concentrations, high humidity, and ambient temperature, or even above ambient temperature, but not refrigerated, so like the worst case scenario conditions. And the loss that you should be less than 5% over the overall concentration. The stability before the sampling is only necessary if you have coated filters or something like that. For other samplers, the shelf life is given by the manufacturer. When you finally get your samples to the lab, the most important part is the sample reprocessing. You have a lot of influences there. You have the volumetric devices, chemicals can have blank values, but most importantly, during extraction, elution, desorption, whatever reprocessing your sample is undergoing, losses can occur. So this is really important. You should conduct recovery experiments. How much will you actually find when extracting your filters or your test tubes? And these recovery experiments should show that your overall recovery rate should be greater than 95% and preferably be independent to the actual concentration of the hazardous substances on your filter. And last but not least, we have the analysis method. You should also check for blank values and interferences, but do some basic statistical values for your calibration, such as the variation of your calibration, which is the coefficient of variation as on the slide. You should give the limit of detection and the limit of quantification, and I will remind you the limit of quantification over your overall method should be less than 0.1 times the limit value for the given substance. And yeah, now you've got a measurement result. You've done your utmost to ensure this result is valid. This is the most trustworthy result you can obtain. But still, some measurement uncertainty remains, and how you can calculate this is actually part of the next talk given by my colleague Cornelia Wippich. I've reached the end of my presentation. I thank you kindly for your attention, and I'm open for your questions now.